Happy New Year, everyone, and welcome to the 85th year of the Kalamazoo Astronomical Society. It is great to see you all here tonight. Have not been in the best of mood this week, but looking to have a little bit of astronomical fun and perhaps a few fun jokes I have here to share later, or a few little fun gimmicks. I was hoping to start off the meeting by sharing a cool astro photo. I've been trying to image the Orion Nebula, do a deep shot of that with the Takahashi on the remote telescope, but the weather keeps interfering out there. You know, it's been mostly clear out there, but not totally clear. So that's kind of been getting in the way. So I was hoping to share that, but not quite. I do know that with the Takahashi, for every image of Orion you take, there is satellites in the picture, every single one. They could be geostationary, but it's hard to tell. But man, they are annoying. So we have an excellent guest speaker here tonight, and normally I do the introductions, but I'm going to hand it over to our brand new member at large, Kevin Jung. So Kevin, go ahead and take it away.
All right, thank you, Richard. Yeah, tonight's speaker, Dr. James Ashley. He's a West Michigan native, grew up in Grand Rapids. He's had a lifelong interest in the sciences. He was a member of the Grand Rapids Astronomy Club, a former past president like I was, and one of its most skilled astrophotographers. We spent a lot of time up there at the Vane Observatory. He ended up getting his bachelor's degree from Grand Valley State and went on to pursue his master's from Michigan State. After that, he worked for a variety of environmental companies doing hydrology and geology, and finally made his way out west, where he got his PhD at Arizona State University and focused his attention on outer space and the planet Mars. While there, he formed a company called Sky Safari, which gave astronomy tours to the local, I don't even remember what the name of it is, local resorts. Yeah. When he completed his doctorate, he started at Jet Propulsion Laboratory. He's been a science collaborator with the Mars rovers. He was a research associate with the Mars Spaceflight Facility. He's gotten several NASA postdoc research grants. He formed back in, can't remember the year.
2000.
Minor Planet Research, which was looking for near-Earth objects, and actually got a grant from the Planetary Society. He's currently working at the Jet Propulsion Laboratory on the Mars InSight mission. He also, in the past, worked with the Lunar Reconnaissance Rover, or Lunar Reconnaissance Orbiter. He's done a lot more, but I'll let it go now, and just please everyone give a warm welcome to Dr. James Ashley.
Thank you all. Thank you, Kevin. It's good to see you. And thank you for hosting me. As Kevin mentioned, I'm a West Michigan.
Sorry about that. Hang
on. Can you hear me?
Yes, you're good to go.
Okay. I don't know how much of what I said before you heard, but I was basically just saying thank you to everyone, and thank you for hosting me. And also just wanted you to know how impressed I am with the KAS website and the things that you've been doing. I, as Kevin mentioned, was a member of the Grand Rapids Amateur Astronomical Association for many years, dating back to 1979. but I never had the opportunity to participate in what you folks were doing. So it's really good to see that and to be included in it and be part of what you're doing tonight. I thought what I would do is give a somewhat formal presentation on the subject of the InSight lander to explain what it is that the mission is about, starting with the science objectives of the mission, and then discussing the instrumentation on the spacecraft, and then giving you an update on the results of the mission so far. And I'll start this discussion by telling you that I just learned about 30 minutes ago that we just got awarded our extended mission proposal from NASA. And so our mission is extended an additional 2 years from everything I'm going to show you here, which is awesome because primarily what the mission is a seismometer. And as you know about seismology, what you're doing with a seismometer is you're listening. You're just basically listening and waiting. You're waiting for things to happen. And you never know when that's going to be. You never know when you're going to have an event worth recording. So having the nominal mission be 2 years long is awesome, but that 2 years has been completed, and now we're looking forward to an additional 2 years of listening to find out what's going to happen next. So let me get you started by sharing screens and asking if you can see the slides. Let me do this. Oh, let's see. My participant screen sharing has been disabled by the host. Is there a way that that can be?
You should be okay now.
I can see you just fine.
Okay, let's see. I've got some slides here. I'm going to try to walk through a PowerPoint presentation.
Yep, you can see it now.
Yeah, it's
Is that
good.
working?
It's good. Yes.
Okay, good. So I don't know how much you're familiar with. I'll just step through all the details here. This is the InSight spacecraft. It's the first mission to thoroughly study the deep interior of the planet Mars. As I'm sure you're all aware, there have been many a mission launched to the planet to study the processes that occur at the surface of Mars. We have orbiters that monitor the current situation on Mars, and we have recorded a number of ongoing phenomena in progress, like this dust devil that you see in the upper right or left portion of the frame. That is a high-rise photograph from the Mars Reconnaissance Orbiter, and you can see the shadow of that dust devil as it towers almost straight up from the surface into the atmosphere. On the upper right side, you have a dust avalanche occurring in progress, captured by, again, the high-rise camera. Other images here are reflecting the Pathfinder mission, the first rover sent to Mars back in 1997, lower left frame. And then the Mars orbiter, or the Mars exploration rovers, the MERS, MER-A and MER-B. There are a great many images to share from that mission, which was designed to last for 90 days and ended up lasting 15 years. So the surface of Mars is known to some extent, and of course we're sending another rover to Mars as we speak. It will land in February, the Perseverance rover, and that one will be seeking out, selecting, and caching samples of surface materials for eventual return to Earth. So that's a whole nother topic for discussion that we might consider at some point. But we have not yet successfully addressed the interior of Mars. That was done, it was attempted anyway, back in 1976 with the Viking landers. Both Viking missions had seismometers on them. But what we didn't know at the time, and until we landed, was that the winds on Mars create a lot of noise. And so it was understood immediately that the data from those seismometers was completely useless. And that if we ever returned to Mars with a seismometer, we would absolutely have to set it down on the surface of the planet and probably cover it with something to shelter it from the noise of the environment. Okay, so what are the things that we're trying to solve? What do we want to understand that we didn't understand before? Well, the model that we have for our solar system's formation, primarily, formation and evolution. And the model that we have is basically a stellar model, right? It is informed by what we see in H2 regions and stellar birthplace nebula, where a proto-solar disk will accrete planets as the star in the center of the disk is in formation. So that the things that end up becoming planets are basically the stuff that didn't make it into the star, right? Now, the process assumes that interior region of the protosolar disk is pretty homogenized. It's all mixed together. It's all mixed up. And that notion is consistent with what we see when we look at primitive meteorites, our carbonaceous chondrites. In particular, the C1 carbonaceous chondrites are chemically identical, really, to the solar photosphere, with the exception of the lighter elements. Pretty much everything else, all the magnesium, calcium, iron, copper, lead, well, not lead, nothing heavier than nickel. But the other elements will fall on a 1-to-1 correlation line with what we see in terms of abundance in the solar photosphere. So our assumption going into our planetary model is that everything was mixed. It was all the same. It was basically carbonaceous chondrite material. And then it changed. As the stuff gets together, it accretes and gets larger. And a couple things start to happen. You have interior heating, both as a result of just the friction from accretion. Gravitational settling creates a great deal of heat. We know this about stellar evolution too. When a sun goes into a red giant stage and it runs out of fuel in its core and the core collapses, that's the process that basically creates the heat that wafts away the outer layers and turns it into a planetary nebula. It's from gravitational settling and the production of heat from the friction of that process. So that's creating heat in these planetesimals as they form. And the impact energy of accretion creates heat. But there's another thing. New stars and planets tend to form shortly after local supernova events. And the supernova events that occur in those clouds are creating a great many new elements through nucleosynthesis. And a lot of those elements are short-lived radionuclides, okay? So they get incorporated in the next generation of stars fairly quickly. I'm saying within 10 to 100 million years after the supernova events have occurred, that stuff will find its way into the next generation of stars. So that's not much time, and you're creating a lot of heat when those short-lived radionuclides decay. So even a small planetary body early on in the history of the solar system, before those radionuclides became extinct, which a lot of them are now, even a small body could pretty quickly heat up and start to melt. And there's another mission that JPL is involved with called Psyche, where we're going to be exploring the metal core of a planetesimal when we launch in August of 2022. That's a whole nother topic. But it's all related. All of this that I'm discussing is related. And what does it have to do with InSight? Well, the model that we have, as I say, it describes the way these materials come together and start to differentiate. When you heat them up to the point of melting or partial melting, the heavy stuff, the heavy elements, the iron and the platinum and the silver and other elements will sink to the core gravitationally. And when they do, they create more heat and actually lubricates the process and eventually form a core. That's why we have an iron core. And they leave behind sulfur-rich materials and lighter elements. And eventually you get this layered differentiated planetesimal that is chemically quite different from its original composition of the carbonaceous material. So now you have a crust, you have a mantle, and you have a core. So that's a process that makes a lot of sense, and we think we understand it. But we've only examined it in detail for the Earth, which is a seismically active body. And we have plate tectonics on the Earth that generate a lot of the quakes that produce the seismic signals that we measure. And we've also looked at the moon. We had seismometers on the moon from the Apollo years for about 5 years. And of course, we have samples of the lunar crust. So we're able to use all that to help put constraints on our model. And so we have an idea for what happened with the moon and what happened with the Earth. But Mars is still this gap. So InSight is a seismometer primarily, and we'll take a closer look at the instrumentation momentarily. But we're sending that to the planet Mars, not only to get a sense for what's going on in the interior of Mars, but to then use that information to constrain our models that will help us understand the process of stellar formation and planetary accretion, not only in our own solar system, but also in extrasolar systems as well, which we're now getting much more information on. So there is a far-reaching understanding that we can extrapolate from just a single seismometer that is fortunately placed and has the right kind of sensitivity on the planet like Mars. Okay, so as discussed, 100 years of terrestrial seismology and geology for the Earth has taught us what we know about the interior of our planet. And then from 1969 to 1977, the seismometers from Apollo and the return rock samples have been informing our understanding of the moon. So with Earth, we have a liquid outer core, solid inner core, and the motion and basically convection within that liquid outer core in combination with the solid inner core produces a magnetic field. I think if it was all liquid, one of the papers that I read said if it was all liquid, you wouldn't have a magnetic field. You have to have kind of both to get the dynamo effect that produces our magnetic field. And then, of course, our planet is active with volcanoes and earthquakes and plate tectonics. We know that here, living in California. It is both interesting and scary at the same time. Then for the moon, it appears to be, because of its smaller size, it has had an opportunity to cool off pretty much throughout its interior, and now it's a dormant world. It does have some evidence of fairly recent shrinking, and that is evident in the form of thrust faults that we can see and wrinkle ridges in some of the Mare deposits. That's evidence that in recent epochs, the moon has been shrinking, probably as a result of further cooling, because as you cool, you shrink, right? And that's effectively, but it's a recent activity, but it's not dramatic, and we can think of the moon as effectively solid throughout, and it has some remnant magnetism, but it's not currently magnetic as in an active way. Okay, so it's quiet, and most of its activity was in the past. Well, Mars fits in nicely between these two worlds. It's big enough to have experienced some active history in its far past, but is it currently active? It's small enough to lose its early heat, but has it lost all of its heat? These are important questions that would help us constrain our model. So it's kind of a Goldilocks planet there, right between the moon and the Earth. And so it's a perfect target. It's accessible. We can get to it. We've done it before. We know how to do it. So let's send a spacecraft to Mars and try to get more information. The proposals to get InSight to fly actually were in work shortly after Viking. So basically, this has taken about 40 years to get the planet, to get this spacecraft off the ground and onto the surface of Mars. So again, you've got some decent constraints on the interior of the Earth. And of course, we can't see any of this. It's all done from seismology. It's all done from understanding how waves interact and refract and reflect off of layers of different refractive index, okay? So you've got your upper mantle. It's separated into the asthenosphere on top, and then the lower upper mantle. And then you've got the lower mantle. You've got the crust at the surface, then the fluid outer core and the solid inner core. On the moon, you've got a crust. It's primarily, well, it's basalt and it's anorthosite. Anorthosite is a plagioclase feldspar-rich material that floated to the surface when the moon was a magma ocean back in its early history. And then the darker deposits, the mare that you see are the basaltic materials. And then there's a mantle, probably, and a core for the moon, and we probably have some idea for the size of that. But Mars, you see, has question marks. We really don't know what these depths are. We don't know the thickness of the crust. We don't know the thickness of the mantle or the core. So those are the things that seismology can answer for you, even if you have only a single station for your seismometer. Ideally, you'd like to have several, right, to triangulate and get better resolution. But even with a single one, you can accomplish a great deal, as we will see. Okay, let's see, can I close these? Yeah. So these are what we want to try to do. These are the vital signs. We want to go there sort of like a doctor would and explore the structure of the crust and its interior. We want to take the planet's temperature and we want to test its reflexes. So these are, in effect, the science goals of the mission based on the discussion that we just had. What is the size of the core? What is its composition and what is its state? Is it liquid, solid, or is it a multi-phase situation? What is the thickness and structure of the crust? And the structure of the mantle and its composition? And how warm is the interior? And how much heat is flowing out at what rate? So the measurements we want to collect to do all this are these. How powerful and frequent is internal seismic activity on the planet, and where is it located within the structure of the planet? How does the planet react to meteoroid impacts? Because we have seen those from orbit. We've seen the effects of recent meteoroid impacts. I think we're up to something like 1,000 or more of these sort of basketball-sized impacts. They create quite dramatic effects on the surface. We can see them very clearly from orbit. They should be measurable from a seismometer with the sensitivity of the one I'm going to show you. So we're listening for those because they will help. That is a source of seismic signals, and it will help inform the questions that we're trying to ask here. So how does the surface of Mars flex as the moon Phobos passes overhead? Phobos is close enough to affect basically a tidal gravitational interaction. What is the spin rate and the wobble of Mars? Because that's going to help us understand its interior. Think of spinning a hard-boiled egg and spinning a raw egg. They behave very differently depending on the character of the yolk inside, right? So that is just basic geophysics something that we can learn about again with the instrumentation on the spacecraft, instrument called RISE, which I will explain to you shortly. And we want to know what the temperature profile is with depth. We want to get the heat coming out of the interior, and we also want to determine what the thermal gradient is, because knowing both of those things informs a lot for our geophysical models. And of course, all of these, they're not neatly separated, they inform each other. So there's a lot of overlap. Okay, so what are the instruments? What do they need to be? We need to have a seismometer, and the one that we have is called SEIS. It is a French instrument. It's built by the French Space Center. And they put together a consortium of other international actors who participate in the mission. Some from Germany, some from Switzerland, from Spain, and from England. So it's a truly international mission. And I was the Deputy Science Operations Coordinator for this mission. So part of what I did early on, well, when I first joined JPL, I was working as a postdoc, and one of the things I was doing was landing site selection work for both InSight and for the Mars 2020 mission, the Perseverance rover. And then after I got hired on, I worked for the Mars Program Office for about 18 months before coming back to InSight and working as the Deputy Science Operations Coordinator. So one of the things I was asked to do, because of my background in science, was to help the science teams understand the various tools they were going to need to use to request the science measurements that they need. So there were several trips to Europe involved here. And we'll take a look at the French Space Center here momentarily. It's quite an interesting, intense couple of years doing all that. So the spin rate and the wobble of Mars is determined with this RISE system, and that is simply a kind of a transponder that can measure the distance from Earth to the spacecraft to within 10 centimeters using Doppler capability. So you have to have a direct line of sight for the signal, and then there is a way to get that distance. And of course, monitoring that over time allows you to very accurately determine what the spin rate and the wobble of the planet are. And those tell you something about the interior, like with the spinning egg. And then this HP3 probe is the first attempt ever to actually drill below the surface on Mars to get some information from the subsurface, and we'll take a close look at that instrument here shortly. Okay, so these are the various tools on the lander. Can you see my mouse arrow?
Yes. It's lightly visible.
Okay, and by the way, does anybody have any questions? If you do, we can always pause. Let me know if I'm going too fast or too slow. Okay, hearing nothing, I shall proceed.
Going good.
Okay, so this is the instrument deployment arm. And as I said earlier, we can't allow the seismometer to sit on the deck of the spacecraft, not with this mission. We have to get it on the surface somehow. And so we actually have an arm here for doing that deployment. The spacecraft may look familiar to you. If it does, you're probably thinking of the Phoenix lander. The InSight lander is basically the same spacecraft. In fact, I think some of these parts, including the arm, were seconds from the Phoenix mission. They were flight spares, and they got cannibalized here into this mission to save costs. So the Phoenix lander explored the Arctic regions of Mars, and the InSight lander is going somewhere a little bit milder in temperature. But we have the arm, And we even have some of the same crew members, some of the same team from the Phoenix mission working on InSight because of their familiarity with the instrumentation. So there's a grapple hanging from this thing, and that will grab onto the various components that we want to deploy to the surface. We have a UHF antenna. We have the RISE antenna. There's one here. There's one here. There is a camera on the instrument deployment arm. There is a second camera on the deck. So we only have 2 cameras on this mission. This is the seismometer. It has a wind and thermal shield that sits over it to protect it from the wind. And then this is the HP3 drilling instrument. It has a chamber that gets deployed to the surface and from which the mole, as we call it, hammers its way down with a percussion hammer beneath the surface. And then we have the heat flow probe at the bottom of this, together with the hammering mechanism. And then there are thermocouples basically along the tether that can measure heat at various depths to get that thermal gradient. We also have some auxiliary payload sensors, originally to augment the seismometer to help remove any noise that we got from the environment. Those include a pressure sensor, wind speed and direction sensors, and a magnetometer. So when you put all that together, you suddenly realize, wait a minute, we also have a weather station here. So we can, in addition to monitoring the seismology, we can also monitor the local weather environment, and that's a whole different area of science, atmospheric science, that a lot of folks on the team are pursuing. So here's the seismometer. It's basically 6 seismometers. It's 3 of these very broad baseline seismometers, which can measure displacements smaller than the diameter of a hydrogen atom and are basically as sensitive as any Earth-based seismometer. There's 3 of those, and so they're measuring in 3 mutually perpendicular axes. And then there are these SPs. These are the English seismometers. The VBBs are French, the SPs are English. They are less sensitive than the VBBs, but they are complementary to the VBBs. They're the short period seismometers, and they too are 3 mutually perpendicular axes. So we have 3 of these. They're nested neatly within a soccer ball sized sphere, which gets deployed to the surface and simply sits there on the surface under its own weight. And then that thermal shield goes over it, and that is your seismometer. Here is the insulating enclosure that goes around the sphere. And here is the wind and thermal shield. This is basically chainmail at the bottom of it, so that when it gets dropped on top of it, it makes a very nice seal with the flat surface. And if you hear pings from time to time, it's because I'm also technically on shift as we speak for this mission, and I may be getting messages from my team for stuff that I'm responsible for. But I do have somebody covering for me, so that should not be a problem. But I'll probably have to go right back to work as soon as we're done here. So this is the supporting electronics box, and this is a tether storage box. The tether itself is right here. Obviously, with something delicate like this, you have to be careful when you deploy your instrumentation to make sure that it doesn't become tangled or otherwise hooked up on the deck. So what, you might ask, would cause a seismic signal on the surface of Mars? Well, we already talked about meteoroid impacts, but intrinsic to the planet itself, interior to the planet, there should also be some other seismic activity. We know this because we see faults on the surface that are, telltale signs of structural weakness and offset. And when you have an offset occur along a fault, it's going to make it's going to generate waves, okay, seismic energy. And we would expect most of that to occur in the Tharsis region, where most of the largest volcanoes on Mars are found. But there's another area over here in Elysium that's got some volcanic terrains. And where you have volcanic terrains, you know that you had subsurface magmas in large volumes. And as those cool, they shrink. And so that could be a source of seismic energy and faulting. We also have tides from Phobos, and we have atmospheric excitation. This is a model showing you how the atmosphere should be undulating across the surface. And with a seismometer as sensitive as the one I described, yes, those things should be making a kind of hum on the surface of Mars, as they do on the Earth. Now, also on Earth, we have a hum that comes from our oceans. And when Lockheed Martin, who built the spacecraft, were testing components of the spacecraft in Denver, Colorado, they could hear the ocean, the waves of the ocean striking the shore of California, well over 1,000 miles away. So this noise is very real, and it is part of our world. We generally don't pay much attention to it. However, on the Earth, because the Earth is such a noisy place, seismologically, we're not really able to hear the hum from the atmosphere. So on Mars, where things are much, much quieter, there's an opportunity to discover some aspects of that behavior a little bit more clearly than we can here on Earth. And here's an example of one of these recent impacts on Mars. They're quite spectacular where they occur because they waft away the dust that obscures the darker basalt underneath. So the features are striking, and they very slowly get buried again over time with fresh dust. But you can see here's an image taken in June of 2008, where we do not see any feature, where in August, a month later, there is evidence of a recent impact. So yes, we should be able to hear those kinds of things on Mars. This diagram here or chart is showing you where we would expect Mars to fit in. The measurement, the scale here is measuring Newton meters, which is a way that seismologists talk about the seismic moment of a planet's activity. And so we see the line here for Earth is the red line, and the line for the moon, for shallow moonquakes, is this fuchsia line. And so we'd expect Mars to be somewhere in between these two based on our current models. Okay, so this is what you would see if you could see the seismic energy inside a planet from a surface signal. The waves penetrate and interact with the various layers, as you see here, refracting and reflecting. So if you have a strong enough signal at one location and you're able to wait long enough, those signals should encircle the entire planet and return to you. So that's kind of what we've been hoping for. Whether it takes the form of a large meteor impact of sufficient energy or an interior quake, we're hoping that we get something that's strong enough that it comes around the planet and lets us measure itself twice. If we can do that, then a single station is sufficient to give you the information that you're hoping for. Okay. Okay, and then these are the rise antennas. And when we're building our plans, we have to make sure that the X-band passes that we use, we communicate to these with X-band radio. we have to make sure that the Earth is of a sufficient altitude above the Martian horizon for these passes to register here and make sense with the kind of measurements that we want to collect. We also use UHF for our communication with the spacecraft, and communication and operations of the spacecraft is something that I do on a daily basis, but is not a detailed part of this talk. If you have questions about any of that sort of thing, we can certainly have that discussion. So again, RISE will tell us if Mars is like a soft-boiled egg or a hard-boiled egg. Now let's talk about that heat flow instrument. The full name of it is Heat Flow and Physical Properties Package, or HP3. And it's supposed to take the temperature of Mars. It's about the diameter of a quarter, and it's about as long as your forearm. And it's ideally intended to penetrate to a depth of 5 meters below the surface. So that's a significant depth. Now, while I was working as a hydrogeologist, I think Kevin mentioned in a past life, I was familiar with a lot of different forms of drilling. We used air rotary, hollow stem auger, mud rotary, and percussion hammer. And percussion hammer relies on down pressure. You have to bang on your drilling tool and get it to go down by giving it some downward pressure. This little thing doesn't have a lot of downward pressure, so it tries to compensate for that with multitudes of hammer strokes. And I'll show you exactly how a hammer stroke works here in an animation shortly. But it's designed to measure the heat flow and also the chemical and thermal evolution of Mars. Now, how could we get at the chemical evolution? Well, again, we're talking about radioactive elements acquired during formation to produce the thermal energy and that history of thermal energy for the planet. If you know what the planet is doing today thermally, you can back calculate what its chemical composition would need to have been in order to produce the kind of energy that we see. Now, of course, you have to get down. You can't stay close to the surface because the surface of the planet is influenced by the sun, both on a diurnal cycle and an annual seasonal cycle. You're getting a sine wave of thermal energy from the sun. So you have to get below all that, what we call the skin depth, to measure what the interior heat is doing. Okay, and here is the cutaway animation of the hammer within the probe. And this is slowed down. It would be actually conducting a hammer stroke when we activate it of about 1 every 3 seconds. So if you figure it would be going bam, 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 like that. We are uplinking our plan that will command 500 hammer strokes here as we speak. And we're hoping that the probe will move a little further than it has. As you'll see near the end of this presentation, we haven't really been able to get very far below the surface yet in this mission. We're trying lots of different kinds of creative maneuvers to see if we can change that situation. But it's a difficult business, drilling on another planet. I know from experience, whenever I was in the field trying to make hole, as we used to say, with our drill rig, that there were always problems, and being present was critical to troubleshooting those problems. So you can imagine here how difficult it is to do this remotely on another planet. Having said that, we have made some progress, and we're able to get some useful measurements below the surface of our landing site. So ideally, this mole would get to 5 meters, and we would conduct that over 10 cycles of penetration, cool down, and measurement. So the probe has heaters within it that will produce a pulse of thermal energy that we can then detect from the thermocouples along the tether. Okay, so you would have to sort of put that pulse into the environment and then wait, and a 24-hour period is the heating time, and then there's a 48-hour cooling period that you would go through before you'd start hammering again to get down to your next depth. And we would do this all the way down to our final depth of 5 meters. And then at that point, you would simply monitor. So the probe does work. Here is an animation, or this is not an animation, this is a time-lapse film of a test that was conducted, I believe in England, in a lab, showing the full penetration of the 5 meter depth. It looks like it's glitching a little bit on my screen. I don't know if that's happening on yours. But. So the thermocouples are the little, so there are graduated measurements along the side of the tether that can be used to determine the depth, because basically this is all you know. You know where the tether is, and you know some things about the probe's orientation. There's a tilt sensor inside the probe that lets us know exactly what its orientation is. And based on all of that, one has to calculate what the actual depth is. It's actually not unlike what we'd have to do in the field when we were drilling. We would use a similar kind of process. We knew the length of our tools, so we could tell from that. But we also had to kind of measure off the tape that we would drop inside the augers to determine depth to water and things of that sort. Because you're not down there, you can't see. You have to use indirect means to determine everything in the hole. Okay, so this actually works, but here's the problem. It kind of needs friction with the outside of the mole in order to advance with a hammer stroke. If it doesn't have any friction, it just sits there and bounces around. And it turns out that the nature of the crust, the regolith material that we landed on, has a kind of a crusty nature to it. It's kind of got a duracrust nature to it. It's partially indurated with cement, apparently, on the Martian surface. So if you pound something into it, yeah, it's crumbly, but there's just not a lot of water there, and it just doesn't hang on very well to things. So pounding this mole into it, it actually surprised us a couple times when the mole backed out of the hole halfway and almost all the way at one point. After a hammering session, we looked at the images to see how we did, and this thing was almost all the way out of the hole. It jumped out after going down and making us all think it was going to work. It started trying to back itself out. So now when we hammer, we have to cover it to keep it from doing that. We have to cover it with the scoop on the end of the arm, and I'll show you some pictures of this later. So here you can see the temperature sensors in the science tether, and there's electronics within this to support that. This is showing you your thermal gradient, and these are the surface disturbances from the sun causing all the sine waves from solar energy. And again, this is the depth in meters. You want to get below all that. You're down here in this nice straight portion of the curve where you're not getting any noise from the sun or anything that's happening at the surface. All this measurement would be coming from the interior of the planet. We talked about the cameras briefly. We don't need to do that again. And here's the size of the spacecraft, in case you wondered how big it was. I have to keep reminding myself, because when you look at the pictures, it doesn't look this big. It's pretty big. This was at Lockheed Martin. Now, this is an animation. Oh, it's got some audio here. Let me turn off this cheesy music. Let's see if this works. Okay, good, it's working. You can see the way the instruments are deployed. Be very, very careful with that tether and set it down on a space that we've analyzed at length and determined to be rock-free and flat. And we got very lucky with our landing site. We have a place that has fewer rocks in it than this animation is showing. And it didn't take as long as we had thought it would to select sites to deploy our instruments. So here's the wind and thermal shield coming down. Now, everything you're seeing here actually took many, many weeks to perform. Just because there's so much ground in the loop, as we call it. We need to take pictures after every move we make to make sure everything worked the way we wanted it to, and that all the commands were conducted properly. And doing that takes a lot of time. So you're seeing
had a question.
Yes.
What's the turnaround time from a signal that you give the instrument to place a thing on the ground and you take a look at it? What's sort of the turnaround time for communication and moving something like that?
Good question. It all depends on the distance to Mars, but it varies from, one-way light travel time of 12 to 15 minutes on the short end to, over a half an hour or something like that on the far end. It doesn't become a factor in our planning, but the light travel time, we just make sure that we have, enough padding to cover what we need, and we don't worry about it. We uplink on either X-band or UHF, either directly to Mars or what we call forward link, where we uplink to an orbiter like Odyssey or Trace Gas Orbiter. And then those spacecraft are relays that downlink the bundle to the spacecraft, which then receives it and immediately executes it. It will take that bundle and unpackage it. It will deliver it to the appropriate buffers, and then it will set about to executing the sequences in the order that we gave it, and the priority that we gave it. So some measurements have a higher priority than others. Certainly on a roving mission, you have a lot of priority given to your navigation images, because those are the ones that are telling you if you're in a safe situation or if you've gone off the edge of a cliff, right? So there's a lot of engineering stuff that has high priority over the science stuff.
Right. And I was wondering, what sort of measuring, how do you know that it's done? You tell it to do something, then you got to wait and see if it did it. So
yep.
You have some sort of instrumentation integral to the piece of equipment, or do you use photographs to look at it, or?
Yep, both of those things. We have what are called EDRs, environmental data records, that come down in the telemetry, basically after each orbital pass. So you imagine you're sitting on the surface of Mars and one of these orbiters flies overhead like this, International Space Station. There's going to be communication with that pass that uplinks data and downlinks instructions if they're on that pass. And then, yeah, that all gets interpreted in the telemetry on the ground. And it'll tell you, it's, you know, all the code is there to tell you if a command has executed properly, or whether there is a yellow flag or a red flag about something. Now this is a solar powered spacecraft. And I'll show you in a moment some pictures of the dust that's accumulating on the solar panels. When you have dust on your solar panels, it's reducing the solar array current that you would have, just like any other solar powered instrument. So if that were to suddenly, if we had a dust storm that suddenly produced a high opacity in the atmosphere, for example, and that was in danger of impacting our plan, we would get a red flag warning, and we would be alerted by Lockheed Martin. They're the ones who get the telemetry first. So they're the ones who take a close look at it from an engineering perspective and let us know at JPL if there's a cause for concern. And yeah, we've had to convene a couple of those kinds of meetings from time to time because there are dust events that occur. But yeah, we get to find out everything that's happening on the spacecraft.
Did you have some sort of dust removal instrument or engineering on the vehicle?
I wish we did. That question gets asked a lot. And you know, it just wasn't part of the budget to design something that would do that. Frankly, I think we were sort of hoping that we would have dust cleaning events, because we did get those with the Mars Exploration Rover at both landing sites. Those took the form of dust devils. So dust devil would come across your spacecraft and clean the dust off, and you'd suddenly see a spike in your solar array current the next day. We have not had a single dust cleaning event at the InSight landing site since we landed. We have measured pressure drops that indicate dust devils are in the area, but we have never seen one, and apparently they're not strong enough to mobilize the dust particles. So yeah, it's something we're just living with and dealing with.
Thanks.
And I'm sorry, did you have another question?
I just said thanks.
Yeah, no worries. So, and here's an example of one of the antennas that gets used at the Deep Space Network, which you may be familiar with. These are the 3 locations across the Earth that are involved in planetary communication, engineered by NASA. There's one in Canberra, Australia, one in Madrid, Spain, and this one here is in Goldfield, about 3 hours north of JPL. And this is, I believe, the 70-meter dish. It's a pretty impressive thing to see when you go up there. And of course, the 3 stations ensure that no matter what direction a signal comes to Earth from, we will always have at least one antenna in the proper orientation or configuration to receive it. But then it makes it difficult, you know, you've got a lot of missions going on out there, including Voyager. Voyager's still going on. Now both Voyagers are interstellar probes. They're both more than 40 years old. I got to see Voyager 2 launch with my own eyes back in 1977. I'll never forget it. But it's still active and we're still receiving signal. And, you know, more and more missions out there make it difficult to you know, to get the signals you want. You have to negotiate with all the teams involved to find out who gets that bandwidth, you know, and we've been told, and we expect that when Mars 2020, the Perseverance rover, lands on Mars in February, we're going to have a reduced communication capability just because all eyes will be on that situation until we know that everything is safe and working well. So here was the InSight mission timetable, building the spacecraft. The launch occurred in on May 5th of 2018. The cruise to Mars took about 6 months. And then everything happens automatically once it gets there. The cruise stage drops away. The vehicle enters the atmosphere at full speed. It's called 7 minutes of terror because, you know, that whole time you're just kind of biting your nails. There's nothing you can do about it. Everything has to unfold automatically. The spacecraft enters the atmosphere, gets slowed down with a heat shield. The heat shield falls away and a parachute deploys. Then that slows the spacecraft even further. Eventually it breaks free of the parachute. It falls in free fall for a brief time before the thrusters kick in, and then it descends on its own to the surface. And then only then do you find out if you made it safely. And we did. And we took this little chip with us. It's got 2.4 million names, including the names of my 2 kids on it. It's sitting on the deck. And you can see them, I guess, with a microscope. It's not like a digital chip. It's they're etched into a wafer. Okay, and this is Toulouse, France, where the French Space Center is located. And like I say, I got to go here a couple times to interact with the French team here at CNES, as it's called. And CNES is one of our main players on the mission. So actually tonight, I have to get an email out across the pond to these folks and to everyone else on the science team, indicating the status of our latest plan so that we can have that discussion Monday morning. So let's talk about our launch. This was the launch site, Vandenberg Air Force Base, the first launch of a planetary mission from the west coast of the United States. Before that, of course, it was all at Cape Canaveral, Florida. But now that we've demonstrated that we can do it from the west coast, this is going to happen more frequently. And of course, the reason we needed to do this, well, there was, I understand, a conflict with some other launch vehicle at the time we wanted to launch InSight, but you can't fly over the country. So I think this launch went south along the coast, around the South Pole, back up around to the North Pole before it hung a left and went to Mars. It was a very, very foggy night. It was a night launch. We were all there. We could not see the launch. We could only hear it and feel it. And you can see the cloud cover here. This is all ground fog. Yes.
Why can't you fly over the country?
In case there is a problem, you don't want this material coming down in a populated area.
Oh, okay, that makes sense. Thank you.
Yep. So yeah, we just punched through the ground-hugging fog layer, and then this is a time exposure somebody took from Mount Wilson, I think, which is a short drive from my house here. And I called my mom and my son. This was like 4 in the morning, and I got them out of bed to watch this, hoping they could see it flying overhead, and they couldn't see it. Other people saw it, but I guess it was like faint and hard to distinguish from, an airplane or something that might be flying. So it just didn't stand out. But the skies were clear in Los Angeles. So some people got to see this when it happened. Okay, and then like I say, we cruised to Mars for about 6 months. And we shed the protective aero shield, began the descent. Descent took about 7 minutes. Oh, and here's the speed, 14,100 miles an hour. So you're hitting that atmosphere, even though it's very thin. At the surface, the atmosphere of Mars is about 6 millibars, right? About 6 1,000ths of what you're feeling right now. So the upper atmosphere is much thinner. But at that speed, it's like hitting, something a lot denser than that. And it's creating a lot of friction and heat. So you still need a heat shield. Now, in addition to the InSight spacecraft, we had these 2 CubeSats, these Marco CubeSats that flew along with the spacecraft as relays. So they were able to relay telemetry in real time during that entry, descent, and landing process. That was really cool, and that had never been done before. Each one of these little spacecraft is about the size of a briefcase. Okay, and then here's the InSight landing site. You can see it in context with other landing sites. Here's Curiosity rover. Spirit is here, Opportunity. The two Vikings are on this. Here's the Phoenix lander up here and Pathfinder. So on communication orbitals that are in a polar orbit, they actually pass over the InSight and the Curiosity landing sites. And so we are in negotiations with Curiosity MSL rover most frequently for COM. Why this landing site? It was really determined by the engineering constraints of the mission. And it's also a very flat, very boring rock-free or low rock count area, which is what we needed to conduct the kind of science that we're interested in here. So it's a very boring location, and you can see that from the images. So from the surface of the lander, here are a couple frames shortly after landing. Notice how clean the solar arrays look in this frame. I'll show you momentarily something a little bit more dust covered. And here, the instrument deployment camera, the IDC, is showing you the grapple here. This is the arm in a stowed position. The seismometer, SEIS, is right here with the enclosure over it. And then you can see Mars horizon out here, how featureless it is. So we did it. We successfully landed. It was pretty hair-raising. A few minutes waiting for that, and it was quite an accomplishment just to get there. But then once we got over that and we were able to relax, we deployed this camera once again to conduct a mosaic imagery of the surface of the deck while the instruments were still on it. And we also turned on the seismometer to measure what the noise level was here before deployment. And it was considerable. These solar panels flap in the breeze and they make a lot of noise. But then we were able to successfully conduct the deployment, like I said, over a period of weeks. And here are some, here's an animated GIF file showing a little portion of that. And that's how that was done. You can see how the low rock abundance of this terrain here. We got very lucky with this patch of ground that we landed on. Okay, and then the wind and thermal shield was deployed to sit on top of it. And here's an animated GIF showing some clouds in the area. It's kind of neat. And these frames were taken with the ICC, the instrument context camera. This is the one that's on the deck. And then over here to the left, you can see the SSA, the structure that housed the mole deployed as well to the surface. So one of the things we're going to measure, you know, as this mole hammers is the signal produced by the hammering, because it's not that far away from the seismometer, and we can certainly hear that.
I have another question.
Yeah.
What are those clouds made of? The clouds, yeah, in that screen that we're looking at?
Oh, you have water ice clouds in here.
In here you do?
And you have carbon dioxide.
The
ice.
carbon dioxide, yeah, okay. So is there like a ratio that we know of, carbon dioxide to water ice?
Oh gosh, there probably is, but I'm not familiar with what that would be. I could try to find that out for you and you know, let Kevin know. The ratio of carbon dioxide to water-based clouds.
And I guess that would change depending on where you are on the planet.
And also on the season, yeah.
And on the season too. I think that's interesting. I didn't know there would be such a mix of both.
Yeah,
And I have another question too. So you're talking about all of these different instruments that are involved with this lander, between the satellite dishes on the Earth and your communication devices and the instruments that are in orbit. There's a lot of different instruments communicating back and forth to get information from this lander to the lander and back to you guys. How many instruments are involved in this?
Well, of course, if you want to count all the dish antennas that the DSN uses, I don't know the exact number, but there's a lot of them.
I didn't realize that either. Wow, that's a lot of communication.
Yeah, each one of those stations has a number of dishes. There's 34-foot dishes and 70-foot dishes. All of that is available on Wikipedia, actually. If you look up DSN, Deep Space Network, there's a really nice Wikipedia page that covers it all. And the orbiters, let's see, there's Maven, there's Mars Odyssey, there's the Trace Gas Orbiter, there's Mars Express, although we never used that one. Most of the time we use Odyssey. There's also the Mars Reconnaissance Orbiter. So there's 1, 2, 3, 4, 5 orbiters. And they get used for comm. I mean, they also have their own suite of instruments like the high-rise camera on Mars Odyssey, or I'm sorry, Mars Reconnaissance Orbiter, MRO. But it's all agreed by the community that these orbiters are, communication satellites. So we get to uplink our bundles on these and use them as relays, and then we also get to downlink the data from the various instruments on these relays. So it's a really interesting community. Now, all those orbiters are in their extended mission phases, so we don't expect them to last forever. And eventually, if one of them goes south, it will obviously reduce our capability. But hopefully, if that were to happen, we would have to regroup and try to replace the orbiter with another comm unit. But we're able to get by with what we have pretty well.
That's great. I'll take some time to look at that Deep Space Network. Thank you.
You're welcome. So I'm just going to play this and see if I can get the sound up. We captured some sound on Mars, and this is a self-explanatory video. So I'm just going to play it. Hopefully you can hear it when it starts making noise.
Touchdown confirmed.
Now, one of our English scientists, Tom Pike, who is the PI for the SPs, he noticed an analogy between the InSight lander and the human ear. The solar arrays behave like eardrums and communicate the vibrations of the environment to the sensors inside, just like our ears do to our brains. I thought that was kind of a neat observation. He's a neat guy. Okay, these are images showing the HP3 mole. And you can see this is about as far as we were able to get before it started trying to come back out of the hole. That's the probe that you see there sticking out of the ground at an angle. It's not going straight down, it's coming out at an angle. And you can see the tether there. And we've been using the arm to kind of just hold it in place, keep it from jumping out, and let it maybe give a little push while it's trying to go down. You can give it a little help. And we've been successful in getting it down below the surface now. And like I said, we're gonna try 500 more strokes here in the next day or so. We're all anxious to see what that does. But now we just got our 2 years of funding today. So we're going to continue doing a number of things we think to see if we can improve the situation. If it can, the thinking here is that if we can simply improve the friction, if we can get it past a certain threshold, whatever threshold it needs, for the soil to grab it, to hang on and not let it slip around or bounce in there, it might go on its own after that. So don't be surprised if suddenly one day you find out, oh, the mole is moving again. Okay, so what is the update? We've been on the surface now for 2 years. We've been collecting measurements. And these bullets I've created from a recent assessment of results from the AGU meeting. Normally in December, I'm in San Francisco for a week at the American Geophysical Union meeting. But this year, because of COVID, it's all been done virtually, but it's still been done. And somebody put together a really nice summary of the latest results from the InSight mission, and I've tried to capture that here for you. So, howling winds since June have been deafening the seismometers for the low energy events, low energy seismic events. Now, nearly 500 small quakes, and when I say small, I'm saying below magnitude 4, have occurred and have been measured. But there's an apparent violation of the scaling laws that apply on Earth and the Moon, where 100 magnitude 3 events corresponds to 10 magnitude 4 events. So there's a 10-fold scaling law that we talk about when we talk about the Richter scale here on Earth. But they don't seem to follow that. Quakes at 3.7 and 3.3 have been traced to the Cerberus Fosse region of Mars. It's about 1,600 kilometers east of the landing site. And we can measure the pressure waves and the shear waves very well. And there's other quakes at a 4,000 kilometer distance. And all of this indicates a cool mantle. There have been no large Mars quakes. We have been slightly disappointed here. We've been expecting them and have not measured them. So Mars is a little quieter than we were anticipating, but we're still listening. The quakes that we have measured have told us that the crust on Mars is surprisingly thin. It's either 20 or 37 kilometers thick, depending on which reflections you want to focus on. And that's even thinner than the Earth's crust. Our models would have told us that Mars crust should be thicker than the Earth's, based on its size and its expected history of cooling. But that's turned out not to be the case. Now, RISE has been tracking for over 350 hours of continuous wobble measurements. And those indicate a large radius for the core, 1,800 kilometers, which is over half the planet's diameter. And it's still molten. So that is interesting. We have not measured any unambiguous meteorite events. We're still waiting for those. The mold penetration remains challenged, as you've seen. And going forward here, we're anticipating quieter winds as we re-enter a calm period of Mars' seasonal cycle. Here's some of the InSight team members, by no means all of them. I'll just point out a couple of them. This is Dr. Banner, who is the principal investigator of the mission. Real nice guy. You can see how casual he is in his Hawaiian shirt. Let's see, that's me there. This is Elizabeth Barrett. She's the one that I was working with on the mission. She's got an interesting history. She used to work on the International Space Station. I mean, she was in the mission operations for that and has a lot of stories. This is Charles Yana, who is from he's the project manager on the French side of things. Most of these people, in fact, nearly all of them, with the exception of Dr. Bannert and myself, are engineers. So there are scientists at JPL who do science, but JPL is primarily a robotic mission engineering facility and the best on planet Earth. So I also wanted to show you this. This is Nice, France, where we were having our science team meeting in February. My hotel was just around the corner over here. Beautiful place. If you've ever been to Nice, France, it's just gorgeous. And this is where we were when COVID broke out. So Italy is just around the corner. I think these hills that you see over here are Italian, and Italy was put on lockdown, and we were nervous about getting out of here before they put France into lockdown. And I remember when I got on my flight to come home, there were 57 cases of COVID, and when I stepped off of my flight, it was up to 100 already here in France. So since COVID, I've been working on this mission from my home. Everything we do, we made this transition very seamlessly and painlessly to the COVID remote world, where everything is done as we're doing right now, through WebEx and Zoom chats. And we found out that we can actually do it all very, very easily, because after all, it's kind of what we've been doing all along. You know, we're not in close contact with our spacecraft. It's at a remote location on another planet. We have to communicate through a series of relays and orbiters, and doing things over the phone and our computers is really not that much different from what we've been doing all along. So we're actually very used to this situation. And even after everyone is vaccinated and this pandemic is a thing of the past, I won't be surprised if some vestige of this paradigm survives and becomes a new paradigm for us here. But while we're doing that, the dust is slowly accumulating, as you see on the solar panels. And that is the challenge that we're facing now as we conduct our planning operations on a weekly basis. So now I will open it up for more questions if you have any. Thank you.
Yes, can you talk about the magnetic field of Mars?
Yes, Mars doesn't seem to have much of a magnetic field anymore. Apparently earlier in its history, when it had presumably had a convecting molten core, it produced a magnetic field which is now remnant in some of its surface rocks. Because a magnetic field will do that. It'll induce a field in ferrous materials that can record it.
Right.
And basaltic rocks, which comprise most of Mars' crust, are ferrous rocks. So there are local signatures of paleomagnetic fields in the crust, but there is no dipole that produces a a magnetosphere around the planet that would be sufficient to protect the surface from charged particles from the sun, for example.
Right.
So that is the reason that the surface of Mars is hostile. It's receiving radiation unprotected by a magnetic field like we enjoy here on Earth.
So in that sense, it's more like the moon, as you were saying early in the discussion.
Yes. Yep. Any future human visits to the surface of Mars will not only have to worry about water availability and a thin atmosphere and cold temperatures, but it will have to worry about radiation and then the dust. The dust is going to be a huge problem for anybody who goes to Mars. I don't know if everybody's thinking about that the way they should be.
Thank you.
Yes.
I had two questions. Would it have been worth the effort to design the solar panels to be able to rotate 90 degrees to have the dust fall off?
Wow, that is a really neat idea. Maybe I'm gonna suggest that would be something they should certainly consider on future landers.
Hey,
And-
Jack, you're hired.
And the other question, with talking about all the various missions on the ground and the orbiters, with thousands of radio frequencies, is there any coordination between the United States and the other countries that have got things going to Mars to avoid using the same frequencies that interfere with each other?
Good question. To my knowledge, the DSN has been sort of chartered to manage all the missions, including United Arab Emirates and JAXA and ESA. Although I don't know if we're handling China's communications. Probably not, actually. That's a good question. I'd have to look into that.
Well, given the location and the distances, there would be a narrow band of frequencies that would be primary to use. And so I was just concerned about crowding and maybe somebody using others' frequencies and inadvertently blocking each other.
Yeah, I think it's pretty well worked out what the bands are that people use. And of course, we've been using X band since the beginning of the space program. I know K band was used for a while. We haven't been using it on the InSight mission, but I think the allocations are pretty well fleshed out for everybody. And then of course we have procedures in place for negotiating bandwidth, on a day-to-day and mission-to-mission basis.
Thank you.
So far, it hasn't become a problem, but of course, our landing windows and our launch windows for Mars occur on a roughly 26-month cadence. So you get a lot of players working at the same time, all of whom are demanding bandwidth. So it's not an easy problem. It's challenging. And the more we do this sort of thing, the more challenging it will become. I'm trying to keep all those facilities up and running and active. Australia had some real concerns with wildfires last year that were threatening the DSN facility down there. That sort of thing. When we have an earthquake here, we always wonder if it affected the DSN at Goldstone. And it wouldn't take much to take something out of commission and make it difficult for a while. But we'll find a way to rise to the challenge when they occur and fix everything that needs it. But I do want to point out with regard to the dust, I really like the idea you had of tilting these things. You can see the vanes on these solar panels. Those stand up about 1 centimeter. And one of the things we're wondering is, geez, is that the reason that the dust isn't getting blown off? Because we know there's wind. We can see particles moving around on the surface, on the ground surface, with our camera images. So how come the dust is not getting moved at all on these solar panels? And the thinking is that, well, it's just such a delicate wind regime. This is not like the Earth. The air is very thin. and it moves in a kind of laminar way, not a turbulent way here probably. The wind environment just a few inches above the surface may be very different from what it is at the surface. And having something like a wind vane, or a vane here standing up a centimeter may very well be sufficient to prevent the mobilization of dust particles. And we didn't have those veins on the Mars Exploration Rover spacecraft. And those were the ones that used to get routinely cleaned off. And so maybe that has something to do with it. We don't know.
Jim, about with the dust and Jack's idea, how does the dust compare to lunar soil? Is it sticky? Because I know that it stuck to all the astronauts' spacesuits and everything. And is there a like a tensileness to the Martian dust that maybe preclude it from like just being dumped off?
Good question. There may be some electrostatic property. We always worried about electrostatic adhesion of dust onto things. As you know, one of the things that I study are the meteorites that we've been finding on Mars. And some of those those iron meteorites are really, really clean. They're not only clean, they're polished, and they have specular reflection. And it appears to me, and I've worked with some dust analogs in some of my research, and even here on Earth in the Arizona climate, which is dry, but it's not, it's not as dry as Mars. When things are really dry, dust behaves in strange ways, and you can get it to blow off. I've coated meteorites with dust and then taken a single pulse from a can of dust off and gotten it to completely leave the surface. And I think what we see on Mars is, sure, there may be some electrostatic adhesion, but that dust is very easily cleaned off of a surface. And on the moon, we had particle sizes for the dust that I think were probably larger than some of the dust we're talking about on Mars. We still don't know what that dust is made of on Mars. We've never looked closely enough at a sample of the stuff. We don't have samples of the stuff. That's one of the things we're going to be interested in collecting with Perseverance, is samples of the dust. There's basically two components. There's a near surface component, and then there's a very, very fine grain component that can stay aloft in the atmosphere with very little agitation, very little turbulence at all. Maybe it almost never even comes down. It just stays up there indefinitely. So to answer your question, it's a different animal than the lunar dust. It appears to be less sticky and perhaps finer grained than the lunar dust, although the lunar dust is pretty fine grained too. But it will probably certainly become a real problem for astronauts in a similar way that the lunar dust did. It's going to get in everything. It's going to get in their food. It's going to get in their machinery. It may even be a carcinogen for all we know. There's a lot of unknowns about that dust as a hazard. I participated in a workshop at the Johnson Space Center on dust as a hazard for humans, and these things were the kinds of things they brought up. Are there electrostatic problems with the dust that could cause sparking? And huge problems. These are things we wouldn't know until we got there, which would be a bad time to find out. Unless we bring some samples home and really take a good look at this stuff.
My other question was, you said in the graphic that there hasn't been any large Martian quakes. Could that be contributed to really no plate tectonic activity?
Yes, the kind of quakes, right, and I failed to mention this. Thanks for bringing that up. The Earth's crust, as you know, is broken into a series of of plates. I think we have about 7 major plates here. And those are all moving, the fastest ones move about as fast as your fingernail grows, all right, about 2.5 inches a year or something like that. I think the Indian plate may be moving about 7 inches a year. It's kind of a fast moving plate. But they're all riding on this asthenosphere that has the viscosity of glass, basically. And that's, you know, it's a fluid, it will move over time. And it's moving in response to heat generation within the Earth's interior, and it's convecting. It's actually overturning over a period of millions of years on a time scale of millions of years. And that's causing the plates to move around in the Earth. The Earth's crust is cracked and it's doing that. Mars crust and the lunar crust is a single plate. It has not had enough interior convection to cause it to crack up and start moving in a series of plates. It's a single plate. So even though we do see evidence of faulting on the surface, that faulting is not associated with plate boundaries. It's associated with large magma systems, large volcanic terrains that have produced an outflow of volcanic material as flood basalts and volcanic constructs. And then the weight of that material isostatically readjusts the crust through deformation. Okay, so you'll have places on Mars that are very massive, and as the planet tries to reassume the shape of a sphere after all that volcanic activity, you're going to have deformation and faulting occurring from that. And also as it cools, you're going to have shrinkage, and that will produce adjustments that should produce faulting and seismic energy, right? So those are the kinds of expectations we had. When you look at the Tharsis region, it's shocked with faults for those kinds of reasons.
Okay, we're going to go ahead and make that the last question. So thank you very much, Dr. Ashley. That was fantastic.
Thank you. Thank you. It was my pleasure.
Yes. Alrighty. So as usual, we'll have to skip the snack break. Eat them if you got them. And we'll jump right into the kind of discussion period of the meeting. And we'll go ahead and begin with a president's report as usual. And there were some things I was going to do here, but let me switch back to the gallery view there so I can see everyone. There we go. So I was going to mention, just real quick here, because I've been kind of wanting to do this for fun, is that, you know, I've been president for quite a long time. And I figured after all these years, it's time I have a presidential theme. Okay, you know, like there's hail to the chief, commands respect and stuff, all that. So I kind of thought, what can it be? What kind of theme can I have? And I thought about 2001: A Space Odyssey. Like, no, that's just too pompous, too grandiose. I want something. I'm not looking for respect. I'm looking for something that will make people happy. And I thought about it, and there's only one song that I hear that always brings a smile to my face no matter how I feel, and this week I feel lousy. So here is the new presidential theme. Just give me just a second here. I'll see if I can find it.
Gilligan's Island theme.
Yeah, that's all, folks.
Daniel Tiger.
Oh.
Mickey Mouse theme.
How about the little Martian guy?
RICHARDELL.
Hang on. Did you guys hear that?
No.
Okay, hang on. I did it wrong. Hang on.
It was like the bringer of jollity from the planets.
Nope.
Jupiter.
Hang on. Okay, can you guys see my screen there?
Yes.
Yes.
Okay, here we go.
From Sanford and Son.
I thought you were going to do Floyd.
Does that mean you're the junk man?
Okay, I was going to play a little bit longer clip than that, but I have always loved that song. It always makes me a little bit happy, and this week we could use a little bit of happiness. So there is the presidential theme. Maybe I'll play a little bit more next month. And I wanted to just take a quick poll real quick if anyone has anything, but did anyone get any astronomical gifts? Here's mine. I got me a pair of 10 by 50 Orion Ultra View binoculars because I figured, you know, I'm pushing geezer age, so it's time to get some old people binoculars. So, you know, instead of 7 by 50, 10 by 50 are old people binoculars. If you don't know why, you'll find out in part 3 of the lecture series. So I got, these are a little wider than standard 10 by 50 binoculars, and I briefly got to check them out one clear night, and they seem okay, but eventually I'll try to write up a report, maybe a quick little report for the newsletter. So anybody else get any binoculars, telescopes, eyepieces, cameras, filters, anything like that?
I received a copy of our last guest speaker's book.
Oh, I have it on the bed over here, so I can't grab it. So
Yeah.
I got one too.
I haven't read it yet, but I'm going to.
Me either. Too busy. Anybody else? Nope. Okay. Well, geez, not very too many astronomical gifts out there. Another quick update. I believe I showed a picture of this that I tweeted a few months ago, but I wanted to give you a Roadrunner update. I tweeted the picture of the Roadrunner on the lamppost at Piishi Observatory, and I asked Mike to get a picture for me, but Rick Benno, who's I think hiding off camera there, got a picture for me. So there he is. So
Nice. Where's the coyote?
If you go back, I know, if you go back about 2 months, you can find the picture of him nestled up on the light fixture, but you really can't see him very well. But he looks like a Roadrunner, and so he's about ready to run to this Acme post here, obviously. And according to Mike, the mouse population has gone down quite a bit around the observatory, so he's worth his weight in gold. I say we keep him.
Yeah. Mascot.
Yes.
Sure.
And so speaking of Mike and Rick, they reported that they gave the primary mirror of the 20-inch a cleaning, so it's nice and sparkly now, which is good because hopefully pretty soon here we're going to get a new flat field screen. We went ahead and purchased a state-of-the-art flat field screen for the 20-inch because the homemade one that we're using just gave really, really long exposure times for the narrowband filter, so we definitely needed something brighter. And we hope to have that up soon. I'll show you what it looks like eventually, but it's just basically looks like a big square whiteboard, but it turns on and gets really, really bright. And for those of you that do use the remote telescope, I will send you a new user's guide very, very soon. I just got to lay it out. That's pretty much all that needs to be done, and then I'll send that out. It's fairly expanded from the first version. And I will do a training video, hopefully in the next few weeks or so, when I get some time and figure out the software, so I don't have to keep holding live training sessions over and over again. New users can just watch the video and get right to work on the observatory. And I just wanted to summarize what I mentioned in the newsletter in my kind of year in review. Of course, with all the bad news, we had one bit of good news last year, is the membership reached an all-time high of 191 memberships. I mean, before last year, we never hit 180, but we blew past that and surpassed to 191 memberships. So counting families as two, we probably have nearly 300 members with, you know, with the families as two and the kids in those families. It's got to be 300. So I got to show you one thing here, which I forgot to open that. I thought I had that open too, but I probably closed everything when I was doing, trying to figure out the silly Zoom thing, which I never did. And I think I have to try that again. So I just wanted to share this with you. This is my been keeping track of this for a while now. So this is my Excel graph of membership since 1997. And not only do we have the highest level here at 191, but it was our largest increase in from one year to the next since 1997. 2017 came, or 2016 to 2017 came pretty close, but 2019 to 2020, the number of people we picked up last year was bigger than what we got in 1997, because this was around when new members started to join. We basically had like a new sort of renaissance in the club, and membership really started increasing.
Hail Bop.
Yeah, Hail Bop helped. Hail Bop and Hiakatake. So there you go. So that's the graph of membership over time. There are a few dips, but nothing really huge. You can see the overall trend is up and up and up and up and away. So hopefully we haven't hit the ceiling yet. There's still plenty of room to expand. And I always look at the list of members that never renewed, and that's way over 200. So there's always people we could bring back as well. And I'm just going to mention that if you have not renewed yet, I'll probably send you a hard copy letter. We're getting down to maybe the last dozen or so people I need to chase down. There are some people, we usually lose about 20 a year, and that's pretty normal. So I think it'll be very similar this year. But we have a hell of a good chance of hitting 200 paid memberships this year, which has never ever happened in the history of this club. And some of you have been waiting for a membership card for quite some time. I will try to get those mailed out. I try to wait for as many people to renew as possible so I can send them out at once. So it's the people that take forever to renew that slow things down to get other people their membership cards. So it's all, just remember, we're all volunteer group. It really, really helps to renew so we can, as fast as possible, so we can move on to newer and better things. And those of you that have renewed, I've mentioned, I've sent you a little email, it says, thanks for renewing. Please either update or create a profile. And by far, most people have not. So I just want to encourage everyone to go to the member profile page here. You just go to membership, go to the profile page. You can click on the member profile form, create a profile. Please make it complete. I do mention up here the profiles of blank entries may be rejected. I had one that was so incomplete this week. For the first time ever, I did reject it. So if you are here on the Zoom meeting and have not yet seen your profile that you made this week, I'm not going to use it because there was nothing there. And I would really prefer a picture. That's not required, but I would really like to have a picture for your profile as well. And it has to be in landscape format and scalable to 500 by 265 pixels. Some people have kind of broken that rule, but I try to keep it within a reasonable limit so the picture doesn't take up the whole screen. So just I can show you my profile here. I think this will work. So, just some basic info. Some people have almost a book about how they got started in astronomy for comments, but it doesn't have to be very long, maybe just a few sentences or a nice paragraph or something like that. And again, a picture 500 by 600 by 500 by 265 pixels is fine. So it's just nice to let people know who you are, especially now since we can't see each other at meetings. And, lots of people here showing video, but a lot of people are not sharing video. And, you cannot block your face at the meeting. So why do you block your video when you're on Zoom? We'll be able to see you sooner or later. So go ahead and do that. And I want to give a quick introduction to the 2021 board. I think I just closed the browser, so I was gonna keep that open. But of course, if you don't know me, I'm Richard Bell. I'm the current president. I've been president now for 10 consecutive years and did 6 terms back in the early 2000s. So this is Sweet 16 for me, which is probably, I don't know, what, 15 too many. Jack Price is going to be our vice president. So Jack, give a wave there. He's been vice president for quite some time. Not consecutively for many years, but consecutively for several. Don Stillwell is our treasurer. I don't know if you can see Don wave there. He's the guy that needs a good shave. Hasn't been to a barber in over a year.
And
Of course-
a haircut. That's disturbing.
But of course, it is winter time, and Don always goes full beard during the winter. So that's when you can tell the bad season is here. Aaron Roman is our new secretary, Alcor. Joe Comiskey is our continuing publicity manager. We haven't seen Joe in a few months. He's had other things going on. I think that's all the officers. I don't think I missed anybody. Members at large, I mentioned Dave Garden, Dave Garden's first. This is his second year back on the board after a long absence. Kevin Jung is the one I mentioned early on. He's our newest member at large. And then we have Scott McFarland, who I don't believe Scott joined us tonight. If he is, he's off on another screen somewhere. And Pete Mumbauer's back on the board. He was a newsletter editor back in 1995, then a member at large in 1996, and then dropped off the face of the planet. So that's the 2021 board. You can go to the KAS board member page and meet all of our new board members. But I just wanted to give a special thanks to Roger Williams, because you'll notice for the first time in 20 years, I did not mention Roger's name, because Roger started as a member at large in 2001, I believe. And then until the end of last year, he was our secretary, Alcor. And now Roger has fully retired. So Roger's going to take a well-deserved rest from writing the board minutes every month and have me hunt him down like a dog and send him to me. So Aaron, prepare to be hunted like a dog for board minutes. All right, so moving on. Did anyone want to share any quick observing reports?
A lot of clouds.
Yep, lots of clouds.
Rich, during the meeting, I was auto guiding on M42, and in my little off-axis guider, there was a little satellite going through it.
Oh, wonderful.
Yep, it's looking for you in your pictures.
Yep.
Thank you, Elon Musk.
Yeah.
Yeah,
Okay.
thank you and curse you both.
completed our lunar observations, so I think each of us had like 5 or 6 craters or features to pick up. So that was satisfying, because that's been active more than a year.
Oh, great. Yeah, Aaron, I might eventually, I have 3 observing awards for Aaron, like right over here. I think I'm just going to throw them in a big envelope and I'm just going to send them to you, because it's going to be a long time before I can probably present them to you in person at a meeting. So
Which ones are they?
I haven't opened them because I'm afraid to lose the pen and stuff. So I haven't even opened them.
Aaron, which ones are they?
It's been over a year. I don't remember.
I'll have to remind you, but I don't want to open them because I'm afraid I'll lose something. So you can tell us when I send them to you.
All right.
I think I'm just going to give up and just send them to you.
That's fine. Maybe in a meeting, I'll show off the pins.
Okay.
All right.
Any other observing reports? Okay. Any quick astronomical news and events anybody wanted to share? It has been kind of quiet. Of course, we're just getting done with the holidays, so that's normal.
Was Arecibo before our last meeting or after?
Yeah, our speaker mentioned Arecibo during her talk, actually, because it collapsed earlier that week. So yeah, we talked about that. Thanks for bringing it up. Now I'm depressed again. I'm going to have to break out Sanford and Son again. Okay, so we'll move on here. Here and none. Quick peek at the KAS event horizon is tomorrow. We have a online viewing session, our 3rd of the season and next to last. Right now, the wind forecast looks a little bit better than it did yesterday, but I'll kind of watch the wind throughout the afternoon and make a decision about the status of the session. And if there is a cancellation, I will let you know. But if you don't hear from me, assume good things. But amongst the many targets we'll look at is we'll take another peek at the Orion Nebula, which seems to be the topic of the night. So you can see what the Orion Nebula looks like with the 20-inch, because we'll use it. We'll take a picture of it with the plane wave, and then next month we'll do it with the Takahashi. We have a board meeting on Sunday, January 10th, which of course is this coming Sunday. It'll be our first of the year. If you do want to participate in the board meeting, you know, you're just a regular member, you're always welcome to come. Just email me. I will send you the Zoom ID and password. There's no registration for that since it's closed, just to members. And the beginning of the Introduction to Amateur Astronomy lecture series is on Saturday, January 23rd. Last month, I reported about 81 have registered. It has exploded since then. We're just about ready to hit 200. We have people from all over the world that have registered, not just the US, of course, but Canada, the United Kingdom, possibly some from Australia, but they were worried about the time difference because it will be like 6 o'clock in the morning there, I think. We got several from the Philippines, one from Russia, someone named Olga. I'm assuming it's a spy who's after all of my amateur astronomy secrets. So yeah, she'll probably get all of our amateur astronomy secrets, and guess what? She's welcome to them. I'm gonna spill the beans. I'm gonna tell her everything. So it is not too late to register for the lecture series. Just go to the Intro to Amateur Astronomy webpage located under the activities menu and register. We're going to talk about the board meeting because I think we might want to try to spring for the webinar version of Zoom, especially after the trouble with YouTube that I had tonight, because with 200 people trying to split it between YouTube and Zoom, I think that'll be just too much work. And
before James signs off there, I just want to say thanks to all the scientists and people at JPL that keep science and discovery in the forefront.
Thank you for that.
Hey, Rose. Hi, Rose.
all right, again, real quick, as usual, the deadline for Prime Focus is January 15th. I hope everyone continues to enjoy the member observatory series. I should have about 3 left. There are other members I know of that have observatories, but they, after repeated attempts, have completely ignored me. So I guess they don't want to write an article and share it with everyone. Any other items that anybody wanted to mention? Okay, here are none. Quick preview for next month. We got another
Richard?
Excellent. Yes.
Richard, I didn't know how to unmute. This is Nina.
Hi.
Isn't there something about a conjunction coming up this weekend with more conjunction? Mars, Jupiter, Saturn?
Mercury.
Mercury, sorry, not Mars.
That's right. Yeah, Mercury is going to join Jupiter and Saturn and form like an isosceles triangle. I have that highlighted in the newsletter on the cover page. There's like highlights, and so the exact date is on the newsletter, so you can check that out.
Okay, thank you.
So our next guest speaker is Dr. Jessie Christensen from Caltech. I believe she is originally from Australia, and her presentation is called "Truth is Stranger Than Science Fiction." So it seems a somewhat mysterious title, but it's basically going to be talking about some of the more interesting extrasolar planets out there in the galaxy. And she did have one request for me to pass on is, she likes to highlight or talk about specific extrasolar planets. So if anyone has a favorite extrasolar planet you would like her to talk about, email me. I'll build a list and I'll send it to her as soon as possible. So if you don't have a favorite, maybe go to the Extrasolar Planet Encyclopedia or something, and or just do a bit of research and see if you can find a favorite extrasolar planet, and she will talk about it. Okay. So if there's nothing else, going once, going twice, we will go ahead and adjourn the meeting. We can always hang around for a little chit chat afterwards. So if you want to hang around, you're more than welcome to, but we will officially adjourn the meeting. So thanks everyone for attending. We'll see you soon.
Thank you, Richard.